This is FE Peer Review. The date is December the 29th, 2023. Anthony Baer and the Eratosthenes Experiment. In the last few months, Anthony Baer has put out a pair of videos. It's called Triangulation to Reality, Parts 1 and 2. I'll put a link to Part 1 in the description. In this video, Anthony did an interesting little project. He sort of recreated the Eratosthenes observation. Together with a friend of his, one of them in Michigan and one of them in Florida, they both measured shadow lengths of a stick and then used the difference in the shadow lengths to come to conclusions about what they saw. And I applaud Anthony for his effort in doing this. He also, in his video, indicated he wanted to kind of open this up to discussion and make it a kind of a community project and wanted people to provide feedback and participate. And so that's what I'm doing in my own way, and this video is meant in that spirit. So here's a brief description of the Eratosthenes observation that he was recreating. We're looking at Google Earth here, and at the top of the image we have Alexandria, Egypt, which is where Eratosthenes lived. And down here, where I'm circling the mouse, is Aswan. Modern-day Aswan is where Syene was located. This was a few hundred years BCE. And as you can see, Syene is just above the Tropic of Cancer. So Eratosthenes knew that there was a celebrated well in Syene where on the solstice, the sunlight would shine straight down that well, and there would be no shadow at the bottom of the well. So the sun was directly overhead. Whereas in Alexandria, he could hold a stick straight up, and that stick would cast a shadow. So Eratosthenes, as was typical with the people at that time, believed the Earth to be a sphere, and his interest was in determining the circumference of the Earth. He figured out, through some clever use of geometry, that he could measure the shadow and then get the distance from Alexandria to Syene, and with those two pieces of information, he could determine the circumference of the Earth. That was his goal. And having the circumference, one can easily acquire the radius and diameter as well. So that was the Eratosthenes experiment. This little diagram sort of describes that. We've got the green on the right, that would be Syene, the Syene location. The sunlight is coming straight down overhead, and there'd be a well that I haven't drawn where the sunlight is going down into the well. And then over on the left, we've got Eratosthenes standing with a red stick there. This red stick is perpendicular to the surface where he's standing, 90 degrees, and that stick casts a shadow. He gets the length of the shadow and the distance A, and that's the information he needed. Well, Anthony Baer has done something similar. It's not precisely the same because neither of his two observers is standing at a location where the sun is directly overhead, but really that's not critical to this observation. So he's got a guy in Michigan standing here at the left, and this guy in Michigan is looking at a red line of sight in the direction of the sun, and he's measuring an angle X. And then he's got the other guy in Florida who is looking along this green line of sight, and he's measuring an angle Y. And the two of them measure their angles at the same time, and then they get the distance between them, distance A, and based on that and using a bit of trigonometry, where those two lines intersect, that's where the sun would be, and they can determine the height of the sun over the Earth. So that's what Anthony Baer was trying to do here. Now, there's an assumption at the bottom of all of this that's vitally important, and that is the assumption that they're standing on a flat plane. Anthony Baer is working on the assumption that he's standing on a flat plane, just as Eratosthenes was working on the assumption he was standing on a curved surface. And this is the problem. You can make the same set of data work for both a flat and a curved surface. Here we see the angle Y measured in Florida and the angle X measured in Michigan and the distance A. And if we lay that data out on a curved line that matches the radius of the Earth as it is generally accepted, we find that the two lines are parallel. And I know that Anthony in his video tried to do this and found that the lines weren't parallel. I think, Anthony, you simply were not careful enough in your measurements, if you don't mind my saying so. You need to be as really precise as you can. You know, even 1 degree off is probably pushing it. So try to be really precise with your measurements, and you're going to find that the two lines are indeed parallel, which means that the data you collected, the 2 angles and the 1 distance, are simply not enough to differentiate between a curved and a flat surface. You can make your data work with either assumption, flat or curved. That means you need more information in order to eliminate one of those assumptions. How do you get that additional information? What more data do you need? What you need is a third observation point. Now, one way to do that would be to pick a point on the equator and do your observations on the equinox. So March 20th, 2024 is the next equinox. Here's my suggestion to you, Anthony, and I don't want to make this sound like a lot of work. I'm trying to find a way to do this that minimizes the effort. Basically, what I'm suggesting would take the same amount of effort that you did before with your previous observation. You and your friend would need to do the same thing you did before. Each of you measures 1 angle. No more work than that. The only additional work you'd have to do is a little bit more analysis, a little bit more math work. But you wouldn't have to be like doing a lot of difficult coordination. Now that's if you're willing to follow my one suggestion, and that is that your third point of observation would be on the equator, roughly the same latitude as you and your friend. Now, you don't actually have to put a person there if you're satisfied with the assumption that the sun is in fact directly overhead on the equinox at the equator. If you agree with that assumption, you're comfortable with it, you don't need to put a person there. Now, if you don't trust that assumption, well, you can put a third person down there and check it. Now that's more work, but you certainly can do that. So it's not like there's anything impossible to overcome here. But I'm going to go on the assumption that you're all right with the idea that the sun's directly overhead on the equator. And if you do that, then you're going to collect basically 3 sets of data. You're going to have a 90-degree observation, which is the equator observation. You're going to have a Florida angle Y, a Michigan angle X, and then you can get your 2 distances off of Google Earth. Let's take a quick look at Google Earth. Here we are on Google Earth, and Detroit is up here. Let's do this. Detroit is up here. And Tampa is about there. They're not quite on the same line of latitude. They're about 3 degrees off, but we can ignore that. It's a pretty minor effect. So that there is a distance of about 1,055 miles. And then from Tampa, we'll repeat that. From Tampa down to the equator, following approximately the same line of latitude, we get about 1,834 miles. So you'll want to do that a little more carefully than I just did it now, Anthony. But basically, you can get your distances off Google Earth that way if you're comfortable with using Google Earth. And you can get your overhead 90-degree sun angle because it's the equinox and we're on the equator. And so with that data, you can have 3 observer points. Now, once you've collected your 3 locations, you've got to see what the result of that is. And this is where the analysis starts. There's basically, I see 3 possibilities, and we'll call this one possibility 1. So what we've got are the angles, the 3 angles, and the 2 distances. And if we were to graph them out using the assumption of a flat plane, then you've got a red line of sight, a green line of sight, and a blue line of sight. If all 3 of those lines of sight converge at one spot, they're all looking at the sun, and they all converge at one spot, that means that from those 3 locations, that's where the sun is, and you can measure a height above the earth for the sun. And it works on a flat plane. If that actually fits with your data, then I didn't draw a diagram for the next thing, but the diagram would be that we would assume a curved surface rather than assuming a flat surface. If we assumed a curved surface and used your data, it wouldn't work. The curved surface drawing wouldn't work. I'm not going to bother drawing it out. I'm just going to say it wouldn't work. And you would, as far as I'm concerned, if you are careful with collecting your data, you do it all accurately, and this is the diagram you get with the flat plane, you've pretty much proved the flat Earth. But now let's look at possibility 2. Here's possibility 2, and I had to shrink the image a little bit because it didn't all fit on that nice page. You've got your data that you've collected and you graph it out with the assumption of a flat Earth, and it's possible. You've got your equator line, which is straight up. It's possible that your Florida line and your Michigan line and your equator line don't converge at one point, but that it's kind of a messy thing like this, which means that there's no one place to put your sun that fits with all 3 data points. That's a problem. If you're assuming a flat plane and you get a diagram like this, you can't fix your sun in one location. Your data is telling you that the sun is in more than one place at the same time, which doesn't make any sense. There's one sun up there in the sky, and all 3 people are looking at it at the same time. They've got to all be looking at the same sun, and it doesn't work with this diagram. So this is possibility 2, and we need to keep that in mind. So you draw out your data carefully, and you see if it matches this possibility 2 or this possibility 1. And now there's a possibility 3 that we're going to look at. You're going to take your exact same data. That would be your 3 angles, 90, your Florida angle, your Michigan angle, and your 2 distances, Michigan to Florida, Florida to the equator. You draw it out, and instead of assuming a flat plane, you assume a curved surface with a radius equal to the generally accepted radius of the Earth. And if you do that, and if you're very careful with your measurements, you may, this is possibility 3, you may find that all 3 lines are parallel to each other. And that would fit with the globe Earth heliocentric model. So if, when you draw out your data, it fits on a curved surface, and these 3 lines are parallel, then your data fits the globe model. So those are your 3 possibilities, Anthony. 1, you assume a flat surface and all 3 lines converge at one point. 2, nothing lines up at all when you assume a flat surface. Or 3, you assume a curved surface and all 3 lines are parallel. Your data with these 3 lines cannot match 2 of those possibilities. Your data can only match 1 of those 3 possibilities. And that means that you can eliminate one of the assumptions, either the flat assumption or the curved assumption, with your data set. So if you really want to eliminate one of those assumptions for good, this little exercise here will do that for you. Now, I'm offering this to you as part of your community discussion that you opened up on your video. But I want to point something out, and that's that this is actually a discussion that's been going on for a long, long time. And I mean, of course, for generations, but we're even right here on YouTube in the last few years, this exact problem was worked on 4 years ago. So you didn't open this discussion. You didn't start this discussion. And I don't mean this in any negative way. You didn't start this discussion 4 years ago, and this wasn't the beginning of it. 4 years ago, Bob the Science Guy and Blue Marble Science did exactly what I just described you could do with your friend in Florida. Bob is up in Michigan. Blue Marble Science, he's down in Tennessee. They did 2 observations, Michigan and Tennessee, and they got data for the equinox. It was 2019 spring equinox. They got data from the equator for the spring equinox, and they did this exercise, and they did the careful observations, and they did the diagrams. And I'm not going to bother telling you what result they got, but I will share their video with you. Back in 2019, Blue Marble Science made a video all about that observation that they did together. Here's his video, and I'll put a link in the description. You can see a screen grab here of the Michigan location, the Tennessee location, and then down here is the equator. So Anthony, this discussion's been going on for a while, and I'm glad that you encouraged people to participate, but I wanted to point out to you that you can also participate in what is already an ongoing discussion. I think the first thing you might want to do is look at Blue Marble Science's video, and then you might want to actually write to him or write to Bob and just ask them questions. If you've got questions about what they did, how they did it, if you've got concerns about how they did it, if you think they might have done something wrong, you could raise those points. And then you could try to recreate this as you did, but with that third location. I think that'd be huge. That would be really encouraging. It would be really nice to see somebody from the flat earth perspective who is prepared to kind of go a little bit beyond his comfort zone and pursue this stuff a little more deeply. If you think you can do that, Anthony, I will admire you for it. And if you do decide to do it, I hope you'll make another video all about it. There's a couple of things that might be useful I wanted to mention to you as well. I wanted to share this one resource with you, Anthony, just because it could make your work a little bit easier and faster and less effort. And that's this website called timeanddate.com. What you can do with it is put in your location, Detroit, Michigan. Just type it in there and it'll go to Detroit, Michigan. And then you can also do the same for Tampa or wherever you are in Florida. And then you scroll down here and you pick the date, March. I've set it for March 2024 so that we can look at the spring equinox. And on March 20th, if we go down on the left here down to 20, that's March 20th, and we follow that line where it says 1339. That is solar noon. You see up here it says solar noon, 1339, March 20th. So at 1:39 in the afternoon in Detroit on March 20th, that'll be solar noon. Now it's 1:39 in the afternoon because it's daylight savings and it's because of where Detroit is within the time zone. But that's a quick and easy way to get solar noon. And you do your observation at solar noon, and then your person in Florida does his observation at solar noon for his time. You're only going to be a few minutes apart because you're only like maybe 2 or 3 degrees difference in latitude. So you'll be pretty darn close. It'll be really hard to do it any more accurate than that. You get your observations at solar noon, and you make sure that your sticks are plumb. Make sure your sticks are nice and plumb, and you're measuring on a good horizontal surface. Like if you're using a yardstick 3 feet long, you want to measure down to at least 1/8 of an inch. 1/16 would be better. You do that, you get some accurate measurements that way, and you'll get some really good data. You should have some good material to work with. I hope you pull this off. I will be thrilled to see it. And for the rest of you watching this video, thank you for your patience sitting through all of this. I hope you found it interesting. And if you did, please click the like button and subscribe if you haven't. You all have a great day. Bye-bye.